Good morning, ladies and gentlemen. It's my great pleasure to be at this Cine meeting on new energy to talk about solid oxide fuel cell technology for power generation and chemical production. Before I start, I'd like to thank the organizer for asking me to participate in this meeting and giving me the opportunity to speak today. I also would like to thank Dr. Fabio Fonseca for picking me up at the airport, drive me on the way to Campinas. I love to visit. I'm very glad to be back in Brazil. I love to visit the country, a beautiful country, friendly and nice people, good food. My first time in Campinas. Thank you for having me here, and many thanks for the hospitality. Okay, so let's start. According to the U.S. Energy Information Agency, or EAI, world energy consumption will increase about 30% from 2017 to 2040. EIA projects increase in consumption in all energy resources, with fossil fuel expected to continue to supply most of the energy used worldwide. Since the energy consumption is projected to increase, if nothing is changed, world energy-related CO2 emission will increase accordingly. So what I believe that any energy for the future, new energy for the future, must be fuel flexible and environmentally compatible. That is flexibility and compatibility. In addition, such energy system should have the characteristic of capability, adaptability, and affordability. SOFC have all these characteristics, so to have the potential to serve as the base technology for future energy system. So let me talk a little bit briefly about all these characteristic for the SOFC. In terms of fuel flexibility, as you all know, one of the key advantages of the SOFC is fuel flexibility. The SOFC can be operated on a variety of practical fuel, for example, natural gas, coal gas, biogas, alcohol, and a number of other possibilities. The SOFC does not require CO cleanup, and if you familiar with SOFC, actually CO, carbon monoxide, is a fuel for the SOFC. The SOFC can be operated on practical fuel, either from reformat from the external reformer, or it can be operated with internal reforming. That means the hydrocarbon, for example, can be reformed within the fuel cell. And also it can be operated on what we call direct utilization. That means the fuel just directly fed into the fuel cell. And so as you can see that the SOFC can operate on various operation mode with fuel other than hydrogen. Well, in terms of environmental compatibility, as you know that the SOFC, just like any other fuel cell, there are no NOx and SOx, and of course, a significant reduced CO2 emission as compared to fossil fuel, conventional fossil fuel power plants. In terms of capability, the SOFC, you all know that have been developed for power generation and operate in fuel cell mode. But it then also can be operated in reverse mode or electrolysis mode. For example, in this case, for splitting water to produce hydrogen. And it then also can operate in what we call cogeneration mode, producing both electricity and chemical. I will talk briefly about that later on in my presentation. Well, in terms of adaptability, the SOFC have been developed or considered for a broad spectrum of power generation application, ranging from very small watt-size devices up to multi-megawatt, kilowatt power plants. So it can cover all the various market for power generation, including portable transportation and stationary power generation application. The SOFC have another particular application in space application. The SOFC in open and reverse mode combined with Sputtering process and methane decomposition. It can be used for oxygen recovery for future deep space, long-term, long-duration human exploration mission. And it also been, actually NASA has been selected, the SOFC in reverse operation, we call it FOCE, for oxygen recovery for Mars in situ resource utilization. I know where you know that Mars atmosphere contains about 95 to 99% CO2. So I think this technology is very suitable for oxygen recovery for Mars mission. And this slide shows example of SO stack that's been developed for a company called Stramatech, now actually called Oxyon, and have been, this is a prototype that's been tested for NASA. I believe it will be sent to Mars mission in a year or two. In terms of affordability, many cost studies have been conducted for the SOFC and have shown that the SOFC cost is very competitive. Of course, need to be proven in the future. Most of the cost estimates have indicated about the SOFC stack account for about 30 to 40% of the total cost. The rest is from the balance of plant, including electronic and control. I like to point it out that most of the stack costs study for planar solid oxide fuel cell system indicated material costs account for the majority of the stack costs with the interconnect. I'm not sure whether you know about the SOFC. In the SOFC stack, the interconnect is a component to connect the cell to cell to build voltage. So the interconnect being the largest contributor to the stack cost. Reason I bring that point because I will show you how we are doing to reduce the cost by changing the interconnect design. So the SOFC have been making progress in the last 10 years or so. Many of the applications have progressed to the hardware prototype pre-commercial state for system, especially to the system up to about 200 kilowatt power level. While other applications, especially those at a very high power level, are still at the conceptual or design stage. Although the technology has made significant progress, there's further improvement is required to enable in the three key driver: cost, efficiency, and reliable, to enable the commercialization of the technology. Some of the key issues need to be addressed. I listed out in here. For example, like cell size for large system, cell size scale up for large system, reproducibility, in terms of cost and efficiency, the power density, the material required to build the fuel cell, and life and degradation. For the time constraint, I'm not going to discuss on this detail. But these are the three critical issues need to be addressed for commercialization of the fuel cell. Well, so I believe that in the SOFC could be technology for the future. It can be very efficient, highly reliable, and cost competitive. And it's suitable for direct fuel utilization, and very important, and for a variety of fuel. And then another key attractive feature for the SOFC is the versatile and open temperature. You can select low temperature, high temperature, depending on material and design. And the SOFC in the future will incorporate advances in nanomaterial, thin film technology, microstructure engineering, digital manufacture, and of course, direct fuel utilization. So I'm going to talk briefly some of these advances in these area using some example of the work that we've done at University of California, San Diego. So let's talk about some example of nanomaterial and thin film technology for the SOFC. This view graph shows advanced SOFC stack design that we've been working at UCSD. This design based on what we call the price surface interconnect. This example of the price surface interconnect could have an egg carton shape configuration, just like the egg carton. So this design that incorporates both fuel and channel with the peak on one side of the interconnect serve at the flow channel for the gas on the other side. In this design, this is the price surface interconnect. In this design, we also have a flat metal sheet bonded to the peak of the interconnect with opening for gas access to the cell. And on this flat metal surface, we have notches to serve as the guide for the cell. And here in this stack design, we show that the incorporate conventional, for example, a sinter cell within the stack design. And this stack design, the interconnect, as you can see, that it reduced weight, reduced the height of the interconnect. So to reduce the weight and volume for the absolute stack, and I mentioned, and that resulted in the reduced material required for the interconnect. And I mentioned earlier the interconnect material being the major contribution to the stack cost. So this stack design have the advantage of reduced cost. Not only reduce the volume and weight, but also significantly reduce the cost for the stack. The other advantage is the extension of the egg carton interconnect along with the flat sheet interconnect form the gas manifolding for the cell, for the stack. So this can be extended outside the hot zone of the fuel cell, so it facilitates the sealing and connection, gas connection for the stack. Another advantage of this stack design is that versatile and incorporate different type of cell. So this shows the incorporation of a conventional sinter cell. So this stack also can be incorporated what we call metal supported cell. In this case, the cell is formed at a thin film onto the flat metal this is the flat metal of the interconnect component, and the interconnect is the electrolyte extended over the edge of the cell from the seal. So we don't need a resealing. In this case, we can fabricate it by special deposition technique, for example. So we can engineer the microstructure of the electrode. In this case, we propose to make the electrode that have the columnar electrolyte scaffold, and then decorate it with the nanoparticle of the electrode materials. So how we, in develop this stack, since a conventional cell already well developed, so we focus our work on to develop the metal, metal supported cell on the metal substrate. And we employ the sputtering process to making the metal supported thin film cell, and we use both conventional and also reactive sputtering for the manufacturing of the cell. The reason we select sputtering process because sputtering, as you may know, that it's been already commercialized, scale up, and you can make it in a large area. And we have developed a process, and initially we use a silicon wafer as the substrate to develop the process. And we have developed, defined the various process procedure condition. So we developed dense ETR stabilized zirconia electrolyte, or YSZ electrolyte, fully dense. You can see here the cross-section and also the add deposit surface. We also deposit porous nickel YSZ anode layer. Here show the porous layer, cross-section, top surface. lanthanum, strontium, cobalt, iron, LSCF, cathode material with the Y-YSZ layer here also show the porous structure, and also for another different cathode material, the lanthanum, strontium, cobaltite, perovskite, and so the porous structure. So also this is a whole complete cell deposit on the silicon wafer, and you can see here we have fully dense electrolyte, HGI stabilized zirconia electrolyte, porous nickel YC anode, and then also porous LSC YC cathode. And then we move on to demonstrate the deposition of the sputtered cell on stainless steel substrate. And here, so again, this is substrate, stainless steel substrate. That the anode nickel YC electrolyte, and in this case, we have a platinum cathode. But here we also have the cell deposit on porous. We use a substrate, anodized aluminum oxide, or AO, because it have a very well-defined porous structure, and show that also the anode porous, anode nickel, electrolyte, YC electrolyte, LSCF, YC cathode. So what the before show the performance of the cell, here the TM analysis of the cell microstructure, and you can see here, in this case, we also have what we call the interlayer, that the gadolinium doped cilia to prevent the interaction between LSCF and YSZ. So we have a fully dense YSZ, fully dense GDC, porous LSCF, YSZ, and porous nickel YSZ. Here show the high magnification of the anode and also at the cathode. And you can see that it have a columnar structure. Interesting that they have the columnar with some sort of fibrous decoration onto the electrolyte columns. So what the performance of the, here, example of the performance of the thin film we deposit on the AO, this the microstructure of the cell, and this is the performance at 650 and 600 degrees C, and you can see that we demonstrate like about 2 watts per square centimeter at 650 and about 1.7 watt per square at 600 degrees C. And to my knowledge, that's the best cell performance at this temperature for SOFC-based SOFC. We even get a better performance with different cathode material. And here show the performance between the LSCF and LSC at 650 degrees C. And actually, if you establish that, I think I didn't show it here, but actually one of the LSC cell at 650 degrees, we got about 3 watts per square centimeter. I think that the world record performance for SOFC at those temperatures. Now let's talk, so I give you some example of microstructural engineering and digital manufacture. In the conventional SOFC, especially use the anode as a support structure. The anode is commonly formed from this a random mixture of nickel oxide, and then Ni-YSZ or zirconia, and the nickel oxide then reduced to nickel metal during either before the operation. As you can see that during the reduction, there's some change in the microstructure of the anode. So the anode can become unstable because of the volume change during the oxidation reduction cycle, and that can cause a cracking within the anode structure, and so cracking in the electrolyte. So that the major issue in the SOFC, especially with the cell design based on the anode support structure. So what we like to do is one approach to address these issues to engineer the microstructure of the anode. And one of our concepts is to design the anode structure. So in this case, the anode structure is made of the interpenetration phase of nickel oxide and Ni-YSZ network, and that each of these phases topologically connected within the anode structure as shown here. Then the question is how you do it and how you fabricate this microstructure. So one possibility is use additive manufacturing, for example, additive manufacture, for example, 3D printing. And I give two examples here, the 3D micro extrusion and also aerosol jet printing. As shown in here, the example of the direct write 3D micro extrusion, and also this aerojet printing. For example, in the aerojet printing, the colloidal suspension is atomized, and then the aerosol is formed, then focus, deposit, and then pattern on the substrate. And here some example of the various microstructure formed by aerosol jet printing that from the courtesy of Dr. Cormier from the Rochester Institute of Technology. So these manufacturing technology can be used to fabricate, for example, the micro-engineer anode microstructure. In terms of SOFC fab operation on different fuel, as I mentioned earlier, the SOFC can operate via the external reformation or internal reforming, and also direct utilization. As some of you may know that the internal reforming is an endothermic reaction, and many SOFC developers have been used internal reforming to do the cooling, and actually that significantly improve the system efficiency. However, the most preferred operation for the SOFC with fuel other than hydrogen is direct fuel utilization. We have shown this for sputter cell, and this one shows the direct utilization of ethanol on the sputter cell at 500 to 500 degrees C. So as you can see here, we got a very good performance for direct utilization of ethanol at 550 degrees C, close to 200 milliwatt per square centimeter. But one thing I'd like to show you here, the sputter cell performance on dry methane. Actually, this we caught our surprise too, because at 700 degrees C, we got 2.5 watt per square centimeter with the dry methane. I believe that this is the best performance or ever reported for operation of SOFC with dry methane. Even at 650 on the way, it didn't go the way, but if you extrapolate, it can go up to about 2 watt per square centimeter. And it's been duplicated, and we've been operated, of course, still in short time, only in about 10 hours, and we didn't see any carbon deposition, anything like that. But of course, further work needs to be done to prove in long-term operation on dry methane. Okay, so let me wrap up by talking a little bit about functional capability of the SOFC. We early SOFC mainly developed for power generation. It can be operate on, conventional fuel cell mode, but also, I showed earlier on our direct power generation mode. Recently, there are a lot of work on SOFC in reverse mode, for splitting water to produce hydrogen. There are also some work on what we call cogeneration mode, or SOFC, and in this case, with the methane, you can work to ethylene and with the co-production of power. So in the SOFC mode, with the addition of electricity, water can be split to produce hydrogen. The SOFC also have the capability to electrolyte mixture of water and CO2 to produce hydrogen and CO mixture of syngas. And there are a lot of work going on in this area. We call that the FOEC, or solid oxide electrolysis cell. It's mainly fundamentally based on the SOFC technology. So all the requirements for the FOEC component are very similar to those for the SOFC. In addition, since we have oxygen evolution in the case of electrolysis, the oxygen electrode required to have SOFC need to have stable performance and also perform reversibility in the electrolysis operation. So here example the hydrogen production that I worked on years back. This will show a 10-cell stack operate at 800 degrees C, and with the input about 1.1 kilowatt and produce about, if I can see it, about 3 something standard liter per minute for hydrogen production, and with about 54% water utilization. And as Dr. Fonseca showed the other day, the electrolysis also can be, electrolysis mode also can be used for production of other chemicals. And one example, that the recent paper that that produce C2 hydrocarbon from methane and air using the oxide electrolyzer with the strontium, iron, manganese oxide perovskite electrode. However, there are not a lot of work going on for the production of chemical by electrolysis using the oxide electrolyzer. And last slide I'd like to show is the cogeneration solid oxide operant mode. This case, you one fit the methane, and you get ethylene here with co-production of electricity and heat. Same thing since it's a fuel cell mode, so it general based on the SOFC. The requirement is very similar to the SOFC. One different thing that's required for this cogeneration is you need a different anode material for the cogeneration operant mode because need to minimize the carbon deposition and so promote selectivity for the reaction. And one example here that I found from the work actually done in Brazil by Professor Paulo de Miranda in Federal University at University of Rio de Janeiro, and he used a lanthanum aluminum manganese oxide anode. Actually, he showed it produced ethylene and also from CF2. And I believe that he operated the cell at 850 or 900 degrees C. So in conclusion, I believe that the SOFC, if further development have the potential to serve as the technology base for a future energy system. Future SOFC technology, I believe it can be very efficient, highly reliable, cost competitive, it's suitable for direct utilization, versatile in operant temperature, and will incorporate a number of advances in nanomaterial, thin film technology, microstructure engineering, digital manufacturing, and direct utilization. And like to conclude, say that it also has potential for chemical production, especially hydrogen production. With that, I conclude my presentation. Thank you very much for your attention.